Another thing that I would like to talk about is the correlation coefficient R, and it's a measure of how well the data fits this linear model. And there are properties with this correlation coefficient. It's a number between -1 and 1. And if R equals 1, it means that the data set forms a straight line with a positive slope. If R equals 0, then the data set has absolutely no correlation. If it equals -1, then the data set forms a straight line with a negative slope. Now here are some different pictures of some scatter plots and the R's that would go with those scatter plots. So you can see in this first one that the R is a -0.95 and that the dots form almost a perfect negative slope. Here's an R with a -0.6 and the dots are kind of scattered all over the place. Here's an R of 0 and they're scattered even more. Here's a positive 0.6 and here's a positive almost 0.1. Now what we're going to do is we're going to learn how to use the calculators in class the next day, and how to use this R to help us understand how the scatter plots better. So tomorrow in class I'm going to teach you how to use the graphing calculator to perform linear regression and to find this correlation coefficient. For now, we're just going to look at this example with an anthropology application. The femur length will be the x's, the height will be the y's, and we're going to estimate the height of a human being, and this table shows the results of a randomly selected sample. So the first thing to do is to make a scatter plot as using femur length as the independent variable, and the scatter plot is shown at the right, and it looks like it has a positive correlation. So we have this scatter plot, and then we drew a line of best fit. Now, using a calculator, we get this bit of information and a correlation coefficient of R and the line of best fit. Now, the reason I'm going ahead and show you on the PowerPoint this data is that if I can show you how to read it right now, it will save a little bit of time in class. The calculator is going to come up with some numbers, and if you look at this right here, this is an equation of a line. Y equals ax plus b. Well, it says right here A equals 2.91. That's the slope of this line. B equals 54.04. That's the y-intercept of this line. Then notice right here this R. That's the correlation coefficient. So that data that was just in that chart 2 slides ago, that was put into a calculator. Okay, so it says enter the data into list L1 and L2 on a graphing calculator. That was the data that was in that chart. Okay, so the correlation coefficient for that data is 0.98597. That's a very strong, positive correlation. Okay? And then it gave you the slope and the y-intercept of the line of best fit for that data in the calculator. So here's the equation of the line of best fit right here. Y equals 2.91x. This can be y equals 2.91x plus 54.04. There's your line of best fit. Okay, so the slope's about 2.91. Sorry about that. For each 1 centimeter increase in femur length. So the predicted increase in a human being's height is 2.91 centimeters. The correlation coefficient was 0.986, which indicates a very strong positive correlation. Okay, so a man's femur length is 41 centimeters long. Predict the man's height. So we can use that equation to predict how tall this man is. So we can use our equation that we just found to predict his height. Because if we put 41 centimeters in for x, or L, into our equation, then we can substitute that in to predict his height. So his height would be about 173.35 centimeters. So the height of a man with a 41 centimeter long femur would be about 173 centimeters. Let's try another one. The gas mileage for randomly selected cars based upon engine horsepower is given by the table. So we'll call horsepower our X's and mileage our Y's. Okay, so let's look at the scatter plot. So it looks like it's going to be a negative correlation. Okay, so it looks like the bigger the engine, the worse the gas mileage. Okay, so let's see what the calculator says for our correlation coefficient. Okay, so we're going to find the correlation coefficient and the line of best fit, and then interpret the slope in the context of the problem. Okay, so here's our line, here's our slope, negative 0.149, here's our y-intercept, 47.5. Here's our correlation coefficient, negative 0.916. That's a pretty good correlation coefficient. Okay, so here's the equation right here. Negative 0.15x plus 47.5. Okay, so the slope is about negative 0.15. So for each 1 unit increase in horsepower, gas mileage drops about 0.15 miles per gallon. Okay, so the correlation coefficient is negative 0.916, which indicates a strong negative correlation. So predict the gas mileage for a 210 horsepower engine. So we can plug that into our equation. So using the equation to predict the gas mileage for a 210 horsepower engine, we can just substitute that into our equation, and it's going to be about 16 miles per the gallon. So these prediction equations are great. Okay, here's another one. Here's temperatures. Here's rainfall. Let's see what happens. So if we look at this one, and temperature is X's and rainfall is Y's, and we make a scatter plot of the data, the dots don't seem to be following a very good line. They do seem to maybe negatively correlated. Let's draw the line through the dots and find the correlation. The slope is negative, like we thought maybe. The y-intercept is 103. The correlation coefficient is negative 0.7, which is not nearly as strong as the last few examples that we've had. So the equation of best fit is negative 0.35x plus 106, and it's kind of a little bit harder to draw the line in this situation. We can get dots above it and below it, but it's hard to even pick ones where to draw it. Okay, so we could predict the temperature when the rainfall is 86 millimeters, but it may not be a very accurate prediction because our correlation coefficient wasn't as good as our last examples. Okay, so we can use this predictor, and in this situation 86 is our y, it's not our x, because we're predicting the temperature when the rainfall is 86. But it may not be a very good predictor. So the line predicts that 58 degrees is when the rainfall is 86 millimeters, but the scatter plot and the value of r show that the temperature by itself may not be an accurate predictor of rainfall because our correlation coefficient wasn't very good. So keep that in mind when using this equation as a predictor. One thing also to know is that a line of best fit may also be referred to as a trend line. Okay, let's do one more example. Find the following information for this data set on the number of grams of fat and number of calories in sandwiches served at Dave's Deli. So we're going to use fat as X, calories as Y. Use the equation of the line of best fit to predict the number of grams of fat in a sandwich with 420 calories. How close is your answer to the value given in the table? Okay, so if we make a scatter plot of the data with fat as the independent variable, the scatter plot is shown at the right. Notice that the dots are kind of all over the place, and if we draw a line It's kind of hard to put the line through the dots because they don't really follow a line very well. And then if we find the correlation coefficient and the equation of the line of best fit, notice that our R, once again, is not very close to 0.9. In fact, it's even less than the one that we just did. Here is the slope, 11.1, and here is the y-intercept at 309. Okay, so here the equation of the line of best fit is 11.1 plus 309. Okay, so if we're going to predict the amount of fat in a sandwich with 420 calories, then decide how accurate we think our prediction is. So the amount of fat would be 9.9 grams. So once again, we are 420 calories is our y, and we're trying to get x by itself this time. And so we only got 9.9. The line predicts that about 10 grams of fat, and this is not even close to the 15 grams that the table says. So once again, we had a very low correlation coefficient, and so our equation might not be a very good predictor. So you have to be very careful, and you want to make sure that your equations are only used when your correlation coefficient is a very good predictor.